what is classification? Separation of points, and we have a pre-labeled set of points. What do I mean by pre-labeled? Already we have a dependent variable, right? Based on some independent variables. The dependent is what I call as pre-labeled, right? So already I have some information. That is why I call it as supervised. And now we have a set of points here, a blue and a red, positive or negative, present or absent, buys computer or does not buy, anything. And which one do you think is a good line that separates? Line A or B? Both of them separate the points in a good manner, but which one would you prefer? Most of us would prefer the first plane, and now I'm trying to model something like this. I want two other planes together where I want to show which one is better. So I want to bring about two other lines parallel to this, and so that I can show a metric that, okay, if the distance between this is wide, this is better, and this is small, and this is not better, narrow, and so I choose this. I want to quantify the enhancement or to say which one is better in a good way. Okay. So what are these lines actually? Lines are y is equal to mx plus c is a very simple line, right? Now it is going to have intercept on both the things. These are also equations of those kind of lines or planes, right? Okay. Now, given that the equation of the current line is 2x plus 3y minus 6 equal to 0, what will be the other two lines? This is what exactly is. Just analyze what these lines are, how the equations vary. So if I consider the central line, whatever is on the top will be equal to 1 and whatever is on the bottom will be equal to minus 1. And any point on either sides, right? And any point on the line will be 0, obvious. And so if I want to vary the distances between, now you see here it's 3y and this is 6y and 4y. So by increasing the coefficients, I bring the line, I narrow down the line. Again, remember, y is equal to mx plus c. What did we play with? Not the data, right? We played with, like here it is like a x1 plus b x2, right? The same kind of x1, x2 are the two dimensions. Likewise, we have x and y as the two dimensions, and we have the coefficients like m and whatsoever coefficients. We have one more m and m1 like that, right? So extension of a single line to the concept of planes and so on. So these coefficients bring about the change in that margin. So the larger the margin, the smaller the value. Got this? You can check these things out. So what I want you to understand by this is, we are going to enhance or play with the classifier by playing around with these margins. That is all you need to understand here. Okay. So how do I control this expanding rate? So now consider this rate 0.99 here, right? So multiplying all these by an expanding rate, a value, which I may call it as, many of you would have heard of something called learning rate, step length, or many new terms. Leave all that. We'll come to that later. As of now, you know something like this is what is that controls the margin and the boundary of classifying. So you see, I have added one value, an expanding rate between 0 and 1. And I got this value. So if it's going to be too much, it's going to get very closer. The smaller, it's going to be larger, right? You have got that. Now, what about this error? Now, I'm all about separating these points. Yes, I'm all about separating these points. And I want all the blue points to be on one side and all the red points to be on the other side. So if I have the first line, I see that it misclassifies one point, but the other line does not misclassify any point, right? So if I have a margin, if I'm going to have a margin for the red points, right, and the margin is beyond the central margin, I can leave some tolerable region for the red points. I can leave some tolerable region, some region of tolerance, so that it don't exactly fit to the points, like how we learned in linear regression, right? We should have some tolerance value so that it generalizes better in the future, not rather than being overfitting for the such one situation. We should be able to generalize, or we should be able to handle the trade-off between overfitting and underfitting, generalization and specialization. So there is one border, and there is another border too, right? Here also it's 3 points. So what do I want to minimize? I actually want to minimize this distance. Yes, I want to minimize this. Of course, I have a rigorous derivation after this. All these are just some visualizations which will make you to understand the derivation better. Like how I gave you some visualization for PCA, and then we went into the derivation that would have made it even more clear. So all these derivation visualizations will give you an idea when I go through the derivations. Right? So this is called the large margin, and this is called the small margin. A large margin and a small margin error, very few, the margin error is small, but it has a larger classification error. But here on the right side, all the points are correctly classified, but it has a very small margin. That means in the future, it may lead to a large error, which I call it as a large margin error. How do I generalize this? So this distance here is controlled by what? By those coefficients. So, and I want these values to be smaller or larger?
Small.
Yeah, small. So for that to be small, this thing should be smaller. Yes, because it's in the, if you want me to prove this, some kind of a Pythagorean max will do, I will come close to that when I go in my derivation, right? So let's jump into derivation now. We consider this line L, whose equation is going to be, for each point in x, its equation is going to be um, like this is x1 and x2. So beta x1 plus beta x2, and I have one free coefficient also, ax plus by plus c, which I call it as beta naught, is equal to 0. And I generalize this as all these beta will come together. So I'll generalize this as f of x is equal to beta naught plus all this beta transpose into x. So this defines a plane. Ax plus by plus c is an equation of a plane, right? So this defines this plane. And if I'm choosing 2 points, x1 and if I choose a point, and if x1 and x2 belong to the line, then what will happen for all the values on the line? The beta naught is going to be 0, right? The equation is going to be 0. So the first condition I'm going to check out is, what does this say? What does this mean? If x1 and x2 both belong or lie on L. Okay, right. So let me assume there is a point x, and there is a normal to the plane beta. Beta is the normal to this plane, and if is X is projected on this line. Right. Then what will this distance be? This distance would be, I call it as okay, this is beta star. This is the normal to the plane. So I have a point X, right? And the distance of this point from this normal is going to be the distance of any point on the line minus the distance of this point, which I am having over here, into this beta star. Clear? Any doubts about this? Right. So if a point is going to lie on the line, it is going to be 0. And from this I can get, so beta star is the normal to L. So B star is going to be it's actually the Euclidean root of a square plus b square, that coefficients that. Have you seen this symbol? What is this called? Double line. This is called the L2 norm or the general Euclidean distance that you have. Okay, that is what is represented as this. Now, here I have taken this, but still beta naught is remaining, right? Beta with x naught is remaining. So beta transpose x naught, what will it be? In 1. Beta transpose x naught will be because in 1 beta naught is left out. We are considering only this, right? So we need to consider x with respect to beta naught also. So in this case, beta transpose x1 is equal to minus beta naught. So beta transpose x2 is equal to minus. That's what I infer from 2. And the third thing is, what is this? Beta star transpose. This distance. Yes. This distance. When does this condition occur? This is the case when x does not belong to L. When does not belong to L, this highlights the distance of x from L. So this should be equal to and what is this? Okay. I can simplify this as we know theta star is this is from 1, right? So we get and also we get beta transpose of x naught equal to minus beta. This is from 2. This is from 1 minus beta from 2. That is for any point that is lying on one side of the hyperplane, that's going to give it as plus, and for the other side, it's going to give us minus, right? That's what is the conclusion I have come across from all these three assumptions, right? So what is my ultimate goal? To minimize the distance of the points from that line or from that plane. Or in other words, minimize the uh, distance of the points to the decision boundary. So what do I mean by the sign distance? If f of x is negative, or okay, f of x is negative, then that is xi beta transpose plus beta naught. So if the true class or the positive class, if the class is positive, then okay, let me consider this to be the true class. So if yi is 1, if it is a positive class, then the point is misclassified if it lies on the negative side. If yi is minus 1, then the point is misclassified if it lies on the positive side. Got
Yes,
my
sir.
point? This is the sign distance. So for any point of the positive class, that is on the right. For any point on the positive class, if it is lesser than 0, then it is misclassified. Likewise, any point on the negative side, if it lies on the other side, if it is greater than 0 for the negative class. Yes. So this one should be this quantity for each point, for each point, for all the values of beta and beta naught, for each point, what should this quantity be? What will this value be? negative for all misclassified points and positive for all
Truly classified point.
correctly classified points. For all points M, for all points M, where M is the set of all misclassified points, like blue points lying on the other side or the red points lying on the either side. So whatever it is, for all misclassified points, what am I trying to do with this function? What should this value be? This is actually the distance by which these points are on either, because this is a set of misclassified points, right? And for all these points, the value yi is going to be negative, right? Yes or no?
Yes, sir.
For all the misclassified points, the value I is going to be negative, right? Whenever the point is misclassified, whether it is the positive class on the negative side or the negative side class on the positive side, is going to be negative. And this is the distance between the line and the misclassified points. So I want this value to be
Maximum.
minimal. I need to minimize this entire quantity. So when will this point be minimal? When will this entity be minimal? That is minus I belongs to M. For each point, the value yi x transpose beta plus beta naught this will be, when will this be minimal? There is no point in M when there are no elements in M, right? That means there are no points in the wrong sides. What do I mean by that? All points are correctly classified, by which I mean the data is linearly separable. What do I mean by linearly separable? It can be separated by a linear surface, linear line, or a linear plane. The data is said to be linearly separable, as the example that I've given over here. There are no misclassified points in M. So the value of yi is going to be minimal. Yes. So this is minimal when M is empty. And when will be M empty? When will there be no line on either sides? By that I say that data is linearly separable. Clear? Now I have come to the point that the data is linearly separable. So there exists a line, right? And now I want to minimize this. In order to minimize this, what should I play around with? I cannot play with the data. I can only play with the coefficients,
Slope and intercept.
slope and intercept, which are here, that beta and beta naught, right? So the error with respect differentiating, I can change only beta and beta naught here. Minimize for all set of points beta plus beta naught, the entire set of coefficients, right? So differentiating d, or the error rate, with respect to beta and differentiating D, the error rate, with respect to beta naught. Whatever is the change. What will you get over here? With respect to beta, you will get and with respect to beta naught, you'll get only yi. Okay. Now I want to minimize the number of misclassified points. Given a situation as this, there are so many planes for which I can get M is 0. Yes or no? There are so many planes for which I can get M is 0. For if the data is completely separable, linearly separable, there may exist many planes in case I take a single line. Right? There are infinite planes. So the first possibility is there are many solutions when the data is separable. Number two, if the gap between the classes is small, like assume a situation like this. And you have okay. Now assume a situation like this. If the gap between these classes is small, then this plane starts to what happens? The plane starts to
Misclassify points.
misclassify. So if I move this plane over here, I may get an optimal classifier. But if I move the plane, I should have drawn a better diagram. One sec. Okay. One point is misclassified as the other side. Okay, this should have been this. Okay. A small movement in this point, in this hyperplane, will bring it like this. And no. Movement here should give it like, okay. Okay. So if the plane is very narrow, when the points between the region between the two classes is very narrow, the movement of this plane will make at least one of the points to get misclassified. If you move here, you'll get one point misclassified over here. So, but based on that, if you try to move it and make it to the correct line, you'll get another point misclassified over here. At the minimal value, this plane keeps on oscillating. You will not be able to end up in a zero value, right? You will not be end up in a zero value. So how many points are there? Not how many points. How many distinct groups are there? Two groups, right? One is a set of all the x's and one is a set of all the circles in the middle, right? If I want to separate this, now this, how many dimensions are the points lying in? How many dimensions? After all, it's a paper, right? So it is x on one side and y. So it's just two dimensions, right? Now if I want to separate these points with a linear separator, right? How can I do it? Will any of these separations work? A
No.
two-dimensional line. Can I do this with a two-dimensional line? So what can I do? That is what I am doing this. The second thing, that is increase the dimension. Exactly a kind of an operation that is opposite to PCA. Instead of decreasing the dimension, I'm going to increase the dimension. What do I mean by increase the dimension? I have X, I have Y, right? I need to add one more dimension Z. So to add that dimension, I will add AX plus BY plus CZ plus D. I had another dimension. And by CZ, I mean I'm going to multiply all these values with the coefficient so that all these points in the two-dimensional plane gets transformed to another dimension also. So now it's like you have all these points, X, Y, and Z dimensional. You have three dimensions. What did I do? I have used the transformation function. I multiplied all the values with root 2 or some value to get another dimension. So now on the Z dimension, all these points are lying in such a manner. Right. Now how will I classify these points? Set of points that is in three dimensions. I can classify it using a plane that is one dimension lesser, right? And that's going to be a linear separator here. So you'll get all the points in the bottom, all these circle points I'll get to the bottom, and all these X or the rose color points I'll be getting on the top. This transformation is what is called the kernel trick. So by this, I get a set of linear points where all the a separable line. So this transformation is called the kernel trick. So when the points are cannot be separated, in the sense when the points are linearly inseparable, right? Linearly inseparable, then it becomes a non-linear classification problem, or it is said to be so. When I am not able to separate using a linear separator, I can go for non-linear classification methods. That is different. Or I can go for piecewise classification, whereby I fit different linear lines. Is this visible? I fit different decision lines. So what does this different decision lines look like? The equation of this line will be x is equal to, suppose it is my x and y, right? What is the equation of the x-axis? Equation of the x-axis?
Y equals to 0.
Y is equal to 0. Equation of this line will be y is equal to some 5. Equation of this line will be 2x plus 3y minus 3. Equation of this line will be x is equal to some 5, so on. Right? What are these decision boundaries? What can you correlate it to?
A rectangle or square?
Rectangle or square, but in our machine learning terms, when I say piecewise linear classifier, it should, by now it should have come to your mind. If value of x is less than 5, Then look here. If y is greater than this, then if x is greater than this, if age is youth, this is lesser than that, y is greater than this boundary. Rule-based classifier, similar to a piecewise notation. More number of boundaries, right? If there exists no single plane that can separate it. That is, data is linearly inseparable or non-linearly separable. Non-linearly separable separation can be handled with more number of linear separators. That is what is called as piecewise linear separable classifiers, or a non-linear structure. Or the third way is you transform the points using the trick which is called kernel trick, for which they have kernel functions, which is called the radial basis kernel function, or Gaussian kernel function, or sigmoid kernel functions. There are many kernel functions that is used for transforming this to a higher dimension, so that you can do it with the linear separator, right? So that concept of transformation and how that margin of transformation we learn it in the next class. As of now, we have learned about, we have not yet jumped into the SVM. We are still with a single linear perceptron, right? A single line which will lead to three cases. One, there are many solutions. So it will lead to infinite solution. When the data is linearly separable, there are many solutions. If the distance between the class is very small, right, then you will not be able to arrive between the correct points, or you will be shifting at the minimum value or the minimum error, because you shift a little, you'll get one error. You'll get shift a little, you'll get one error. You will not know which is the very apt classifier, right? And the solutions for this is choose a smaller learning rate or increase the dimensions in the point, so that you will arrive at a linear classifier with a higher gap, right? How to optimize the margin error, we'll see in the next derivation. But at the end of the next class, you will be dealing with the parameters of XPM, that is classification error and marginal error. How to optimize that? That may lead to an optimization problem. That is what is the question. Okay.